All right, so this is the practice exam review for today. Let me go ahead and start sharing my screen so that the people on Zoom can watch that. So this is what we are doing today. Here's your practice exam. All right. So let's start out with the first. So we're going to start out with questions that are basically non-coding, but that's fine. So first question for each of the following questions: indicate which data structure would be best suited to handle each scenario. So let me go ahead and grab this and drag this down and open up the chat window so I don't miss anything. All right. So we've got our choices: array list, linked list, stack queue, tree, priority queue, set, or map. Right? And a map is also known as a hash table, a hash map, a dictionary. Just remember that in Java, it's overall classified as a map. QDOR the Explorer. Okay, so you need to model which patient should be seen next at a hospital. This is extremely topical, but was not meant to be when I wrote it. Speaking of topical, before I continue, today is election day. Go vote if you didn't get the message on Discord. I plan on doing so once I get basically going immediately after I get home from school. So, important. So you need a model which patient should be seen next at a hospital. Patients should be seen in as close to order of arrival, but patients in a more severe situation should be seen first. Which kind of data structure is this? Yes.
That's a priority queue.
That is a priority queue, right? Because we are trying to see people into the order that they appear, but right, people with head wounds should probably be seen sooner than people with a broken toe, because those, concussions are serious business, right? So a router needs to hold packets in a buffer and deal with them in the order they appear. What data structure is this? Don't say it all at once, sorry. Q, that is right. Remember, to pronounce Q, you just simply say the first letter and forget about all the other ones. Right? So buffers basically are kind of the classical situation for queues, other than like trying to, and as well as scheduling. Those are kind of the ideal situations for queues. All right. You need to model a hierarchy. So which of these are best for modeling hierarchies? Yep, tree, because there's somebody at the top of a hierarchy, right? So tree's got something at the top that makes the most sense. But like taxonomical, those are trees. Family trees, those are trees. All right, you need a data structure to hold your previous decisions in case you need to backtrack. Stack, right. The answer is not recursion, it is stack. I'll be very sore if you say recursion is a data structure. It's a technique. Okay. Let's go ahead and do our vocabulary. The node at the top of a tree is called what? Yep. The links from a node to its successors are called what? Multiple possible answers here. Branches and edges. I'll also even accept links, which is what I used to describe it, because everybody will know what you're talking about. It's fine. There are multiple things. Branches is more of a tree term. Edges is more of a graph term, but since trees are graph, that's perfectly fine. The predecessor of a node in a tree is called what? Parent, right? That's the direct predecessor. What would we call like the predecessor's predecessor? Ancestor or grandparent. Both are correct answers. Right, ancestor is a generic term, and as well as descendant, but always feel free when talking about trees to take this and use family tree terms. So nodes that have the same parent are what? Siblings. Yep. So describe using code how to calculate the height of a tree recursively. And remember, I'm defining height as the number of layers of nodes that we have. So how would I know how to define the height? How would I define the height of this tree? Right, this tree over here. Got myself a left tree and a right tree. How do I define the height of the tree?
I'll go left and right, and I would have to check where it could go farthest left and farthest right, and then basically store the biggest height that I've seen.
Yep. So.
And then the height includes the root too.
Yes.
Right? So then you'd add one.
Yes. So it would be so my height is the height of my. So the height again is simply so the way to calculate my height is figure out the height of my left side, figure out the height of my right side. Take the bigger of those and add 1. So, right, it would be, if we were to use some code, it would be, or some pseudocode, it would be height of the max of, you know what? We all understand. Right? So it's 1 plus the height of the max of left or right. And again, I considered this tree over here to be a height 3, and now I consider this to be a height 4, where that's the number of, again, layers of nodes. Some mathematicians consider it to be this way. If you decide to work that way, just make sure you comment that, okay? That's fine. Perfectly, it's okay to have a different interpretation. You just got to let me know that we're working in the same, you just got to let me know so we're working in the same kind of mental space. Make sense? All right, so draw an example of each of the following types of binary trees. Yes?
Is that all the detail we would have to go through, or would we kind of have to say what we do, like let's say once we reach that null node, and then how we would really store the max height and make sure that the max height gets returned?
I mean, we can cover that by just simply saying recursively calculate the height,
Okay.
you know, and also describe what the base case is, which is if I don't, basically, which is that if the node doesn't exist, it's a height of 0. That's our base case. Okay, so draw an example of each of the following types. Use a different example for each possible tree. Now, the reason that I say a different example is because that's to avoid smart alecks like me from saying, so we need a full, a complete, and a perfect. So this caveat in there is to avoid smart alecks like myself from saying, this is full, complete, and perfect. So full, right? What does full mean? Full means that I have either 2 children or no children, every node. So for instance, this is a full tree because it has no children. This is not full, but this is, right? And likewise, this is also full because every node has either 2 children or no children. Okay. Okay. So we'll skip complete for a second because I want to go to perfect first. Perfects fit this nice convenient mathematical definition of basically that we have where they have n nodes where n is equal to 2 to the height minus 1. There's only one possible configuration for that. So if we've got a height 3, then it takes up all available spaces. Right? That's what a perfect means. It's taking up all available spaces appropriate for its height. Okay. It fits this equation pretty well. So that's fine. That's a perfect tree. Now complete is the one that students have the most trouble. I will not ask you to write a function on calculating a complete tree, like to check if a tree is complete, because that is tedious and annoying, and I'm not even sure how I would do it, but because it doesn't really fit with the standard way we would do recursion, because you'd have to do left to right, So, whereas perfect's not too bad. You just figure out the height and then you figure out the size of the tree. Here you would have to, if you write function to check if it was complete, you figure out the height, make sure the layer above was perfect. Then you'd have to like kind of manually check, which is seems a bit annoying. If there's a better way, let me know. But for complete, it's now complete is relevant for when we're packing these things into an array as opposed to a linked data structure. So complete is correct all the way up to the top layer, but then sorry, complete is perfect all the way to the top layer, but then the bottom layer over here is filled left to right. So this is a complete tree over here. If, on the other hand, I remove this node and create a gap, it's no longer complete, right? Because there's a blank space. What we would do is that with a complete tree, you kind of say, this is index 0, 1, 2, 3, 4, 5, 6, 7. And so then we'd have a gap in 8. We don't want that in a complete tree. So this is a complete tree. This is not a complete tree because there's a ginormous gap. Same here. This is complete. This is not complete. For a complete tree, we need left. It needs to be filled on the bottom from left to right. And it's got to be perfect in this layer up. Because otherwise it would have, would have gaps. All right, so draw the binary search tree that forms after inserting the following integers. For the problem, for the multiple choice problems, feel free to write them down and like take pictures of your notes. So if you get it wrong, at least you can always send me your notes to show that you have extra credit. Just be sure to send me your notes like the day of the exam so that I'll try to remember to add an additional question so that you guys can upload your notes there, right? So feel free to use your phones to like take photos and stuff, just not of the exam questions, of your notes and upload them. That's fine. Okay. So 42 is our root. So 10 is less than 42, so it goes to the left. 50 is greater than 42, so it goes to the right. Then 12, so less than 42, greater than 10, so that becomes 12. 17 is less than 42, but greater than everything else, so it goes over here. 80 goes over here. Sorry, 17, and now 80 goes over here. Negative 12 is smaller than everything else, so it goes all the way to the left. 100, that's bigger than everything else, so it goes all the way to the right. 96, bigger than everything until we get to 100, in which case it's left, so we put 96 down here. 105, greater than everything. Very easy to make a careless mistake, so just be sure to double check your work, right? That's the main reason why you would get this wrong. There's only 2 reasons why you'll get this wrong: a careless mistake, or you didn't study in the first place. And you're here, so I don't think that applies to you. So 86. So greater, less than 86. And then 72. Less than. And now I'm gonna go ahead and keep this answer because I was lazy and said, hey, using the previous answer, draw what happens when you remove the following. Because why draw the tree when I can make you do it for me? Makes sense for practice exam. Okay, so we want to remove 42. 42 is the root. It has 2 children. Removing something with 2 children basically means that what we're going to do is that we are going to go and find the next in order predecessor, which is the smallest thing, sorry, the biggest thing that's smaller. So that means going 1 to the left to go into the left subtree and go all the way to the right. That's the biggest thing in this subtree over here. Okay, so 17, and what we do is that we copy over 17 up to here. Okay, and now we say delete 17 from this subtree because we just moved it up here. So 17's over here. Oh, it's got 1 child. Sorry, no, it's got no children, so we can just remove 17. That's no problem. Effectively, we just moved 17 and overrode over there. But it's easier to kind of visualize like that. Now, if we delete 12, 12 is super easy to delete because guess what? No children. 17, well, we just moved that thing up there. It's almost like I'm trying to torture you or something. Okay, 17, what we're going to do over here with 17 is that we are going to erase. So right over here, we've got to erase 17 and we've got to replace it. Go 1 to the left and all the way to the right. And this is kind of constructed to show you that if you go all the way to the right, you're going to end up at 10. That's okay. You went 1 to the left and you couldn't go any more to the right. So 10 is what we copy over here. And then again, we're going to remove 10 from this left subtree. So the way we do that, to remove 10 from that left subtree, is as follows. Well, 10 has one node, so 10's parent will adopt that child. So I'm just going to do that by deleting 10 over here and then deleting that line and drawing a new line going to -12. There we go. And then deleting 96. Again, kind of the same thing with 96. Delete something with one child, you just have your grandparent adopt it. Yes.
I have a general question about recursion actually.
Mm-hmm.
If you have a recursive function that returns an integer and you reach some kind of base case and you do not want to return an integer, can we just say return and go back up the stack, or do we have to return?
You'd have to, if the function for a function in Java, if it specifies that it needs an integer to return, you have to return an integer.
Okay.
So it's the method statement is a promise saying that here we're going to provide these things and this method's going to provide this kind of output. So you can't provide nothing.
So that would only work if it's a void recursive function.
Yeah.
Okay.
Mm-hmm. Okay. So which of the following is the pre-order traversal for a binary search tree? Pre-order means we're going to do the root first. And now we're always going to do the and we're always going to do left and right no matter what. Left always comes before right. The only question is, where does the root node come in? In pre-order, root node comes before everything else. So it comes, so I handle myself and then I handle my left and then I handle my right. For post order, I handle my left, then I handle my right, then I handle myself. Okay. And then finally for in order, I do my everything that's less than the root, and then everything that's greater than the root. So left, myself, right. All right. Draw the min heap that forms after inserting the following integers. So we can ignore the underlying array because remember, heaps always they take the form of arrays, right? But what we're going to do is we're going to pretend we're more interested in the tree structure, right? And just remember that we've got some that for heaps you have a formula that for moving things back and forth. Now remember, heaps are always complete trees, so that's a kind of a key for the way they work. When I was giving this in person, people would have to draw them. The most common wrong answer was they did not have it as a complete tree. But also they don't fall, even though they're trees, they aren't binary, they're not search trees. So they follow different rules. So 8 goes up on top, then 10 goes into the next position in the complete tree, then 50 goes into the next position on the fifth tree. Now this is a min heap. The way it works for min heaps is that when you insert an item, you push it basically the heavier items sink to the bottom and the lighter items float to the top. Okay. And here, the bigger the number, the heavier it is. Max heaps heaviness is inverted, you know, where basically the smaller the number is, the heavier it is. Okay. But this is a min heap, so fairly easy to figure that out. So 8, 10, 50, 20. Okay. So far, no bubbling up and having to swap. Here though, 1 is lighter than 10. So it's going, so what we do when we have a lighter item, and how we know we have a lighter item is we just check against our parent. That's all we ever have to do. We just always check against the parent. So 10 is heavier than 1. So 1 and 10 will swap. And then we just continue until we can't do that anymore. So 1 swaps with 8. Now 1's at the top. So we now insert into the next position, which is we put a 4 in. So 4 is lighter than 50. So 50 and 4 swap. Okay. And now 4 is heavier than 1, so it's not going to float up any further. Make sense? And then finally, we put a 3 in over here, where 3 is heavier. Sorry, 3 is lighter than 4. So 3 floats up, and it stops floating up once we get to 1 because 3 is still heavier. Okay. Every add operation is worst case log of n time because worst case scenario, you have log n steps you have log n swaps to do if you're lighter than everything else. Right? If there's 8 items, then you'd have, if there's 8 items current and I put in -1, we'd have 1, 2, 3 swaps to do. So that's why it's log n. Okay. Because of course log base 8 is, oh, sorry, log base 2 of 8 is 3. So, all right, moving on. I believe I want to keep this because using the heap you drew above, draw the heap after you remove an element twice. And if I do it wrong, please, if you think I've done it wrong or something, let me know. It's possible I make a mistake. I probably didn't. Okay. So what am I going to do here? I'm going to go ahead and swap. So to remove an item, what I have to do is that basically I remove the top item and I take the last item from the heap. And move it here. Okay. Now, at this point, though, as you can see, the heap is not really out of order because the lightest item is no longer at the top of it. So what we do is we compare 4 to its children. So when we remove an item, we move the last item to the top, and then we see, does that item need to sink down? So 4 and 3, 4 is heavier than 3, but lighter than 8. So we're going to swap with 3. So 3, 4, and then 4 can't sink down to, isn't heavier than 50, so it doesn't sink down any further. Now, when we do this part to remove 3, right, because we're doing 2 remove operations, and removals always will remove the top of the heap. We're going to go ahead and put 50 up here. Now, 50 is bigger than both its children. So but in order to keep it a min heap, we swap with the smaller children. So 4 gets to go to the top yet again, and 50 sinks down here. Well, there is to it. All right, so the reason I got mildly distracted is because I was thinking about this part, which I haven't done in a while. I don't think it's on exam, but I'm still going to do this anyway, which is draw a Huffman tree for the symbols. So a Huffman tree, right? That's compression. How many of you watched those videos on Huffman trees? Everybody did? Yep. So Huffman trees are all about compression. This is a lossless form of compression. So basically with these, we want the most frequent symbols to get the we want the most frequent symbols to have the most, the least bits. So I'm just simply thinking for a second because I haven't done it in like 4 years. I'm sorry, and since the beginning of COVID, which feels like 20 years ago. So, all right. So, yes.
I'm sorry. What again is the difference between a priority queue and a min or max heap?
A min heap is a way to implement a min heap or max heap are ways to implement a priority queue.
Okay.
So just in the same way that a linked list is a way to implement a list. So min heaps and so priority queues, you could do those, but min heaps, because they keep the high item with the highest priority at the top, they make it perfect for implementing queues.
Yeah, it feels like it's the same thing.
They are in a way. They're just, it's one. A priority queue is simply a label applied to a min heap or a max heap when you want it to operate like a queue.
Oh, okay.
Okay, so what I'm going to do is I'm going to sort these in order from smallest to biggest. So we have L20 from least frequent to most frequent. So P40, A50, E60. And so here's where, so what we need to do here is that basically we start constructing this Huffman tree by what we do. And what we do for that is that we dequeue the top two items of the priority queue. So and then we put them in, and then we put them under a node together. So X and L have a combined weight of 1 and 20, so it's 21, right? And now what we do is that we reinsert this into we reinsert this node, this combined node into the priority queue. Now, the main mistake I see is that students will put it like right here. It's a queue, but it's a priority queue. Or they'll always put it to the front without regards of sorting it. Putting it to the front in this case is the correct choice. So XL and 21. So now we DQ again, XL and P. So we create a new node. The thing that gets DQ'd first will go on the left, and the thing that gets DQ'd second always goes on the right. It's like riding a bicycle. Okay. So now we have a combined weight of 21 and 40. So that becomes 61, which is bigger, which is more weight than both of these. So that's XLP. So next we do Annie. Okay, can I select and move these guys? So let me go ahead and just redraw this guy over here. XL. Sorry, I need to redraw because I did not plan this out well enough. XL 20. XL. Okay, so now I just simply redrew this on the side. This is a combined weight of 61. Okay, A and E together go here. A has a weight of 50, and E goes next. Okay. So A and E, we DQ those because those were next, and we put them onto the tree like that. They have a combined weight of 110. And they go, and because they've got 110, they're in the back of the priority queue, right? And now we DQ these both and we join them because, and this one goes on the left and this one goes on the right because which one gets DQ'd first? And that's our Huffman tree. All right. Now, when I ask these questions on the exam, but I'm not going to do this on the exam because time constraints on the actual exam. Encode the string apple into binary using this encoding. So we do this in binary with lefts being zeros and rights being 1. I always ask you to do a fruit in these kind of cases. So we do an A. So if we want to do apple, we go to get to A, we do 1 0 for A. Then P is 0 1 0 1 0 1. And then do an L, we do 0 0 1. And then to do an E, we do 1 1. So using this if we get sent this encoding, if we see a 1 0 0 1 0 1 0 0 1 1 1, then the computer will decode that into apple. Okay. Make sense? Again, I'm not going to go do this on the exam just because of the electronic exam, and I haven't been doing it while things are being crazy with COVID. Just simply because I felt that there needed to be something cut during COVID, and that was it. Much as I enjoy it. But all right, now we get into the coding, which is, so first things first, going to create a node class for me. So private static class node for our binary search tree questions. And it's going to just have a node. Yeah, and I'll give it an E. Node E left. Node E right. E data. And then a constructor that just simply just takes in public node. Is anybody else really excited about the Wheel of Time TV series coming out? I'm like waiting for that for like forever. If you don't know what I'm talking about, get really excited. It's I've read the book, include the final book, A Memory of Light, which came out after the original author died, was written by a different author who used basically the copious amount of notes. That final book had a single chapter in the book, and that single had a single chapter that was 300 pages. And that was just a small part of the book. The chapter itself on via audiobook was 8 hours long. I mean, it was kind of, Armageddon, so it made sense that that one was that long, but still, it was long in the making. So I'm really excited. Okay, so this one was size tree, which was, if we look at this, is we are trying to calculate the size of the tree recursively. We do not, our code is we are going to pretend that, there is no size method, which is convenient because I didn't write one here. So, sorry, there's no size like variable. So we're just gonna have to count the nodes manually. So first, let's start off our base case, right? Base case is thus. So base case is either basically null. It's almost always the first thing to look at of the base case, to be honest. Base case for a tree should almost always be, what if the tree doesn't exist? Because that's super easy to solve. What's the size of null of a null tree, of an empty tree? 0, right? So that's really easy for me to solve. And if I do that, and if I figure out nulls like that, it helps me prevent null pointer exceptions. If root, so remember, and root here is the root of the tree or subtree. So it's not necessarily the root. So if root is equal to null, then the size of this tree or subtree is 0. Otherwise, remember, kind of just want to figure this out. I need to figure out 3 things if I want to figure this out recursively, right? Because recursively means I only know about myself. And I know I know where the next steps are, but I don't want to solve them because that's hard. I'm lazy. Okay. So what I need to figure out the next steps for, if I'm trying to calculate the tree, is I've got a left subtree and right subtree. So it's either null or this, where I know I exist, but have no idea about my left subtree or right subtree. I'm a bit too lazy to honestly check. Really should check in on my kids though. That seems like good parenting to know whether or not they exist. Regardless, okay. So I know my size, and I'm gonna be a bit verbose in this exercise right over here, and then I'll reduce it. My size is equal to 1, right? I know I exist, so my size is 1. Okay, and then I have my left child, possibly. So int left size should be how I figure it should probably be, I should figure that out, so I'll figure out what the size is by calling size tree on root.left. So I'll figure it out. I'll ask my left child how big they are. They should know that answer. Again, not exactly the best parenting right over here. Okay, and then I'll do the same for my right child if they exist. If they don't exist, I'll just get 0 right back, and that will answer that, right? So now what I can do is that I said, okay, I've got my left size, my right size, and me. So the total size of this tree would be all 3 of those added together. So return left size plus my size plus right size And as you can see, I could just simply, so this is working solution, but I can also simplify that. I don't need the my size variable if I know it's 1. So I could just simply say left size plus 1 plus right size. Nor do I need these variables. I could just simply replace left size with size tree in the return statement, right? I don't need those variables. So I could actually reduce this to 1, 2, 3, 4 lines if I was so inclined. Okay, so you can make really really short solutions, or if you're really so inclined, you can do like one solution, like one, which is like you could do return what was it, root equals null question mark 1 colon and then size tree left dot size plus 1 plus size tree, sorry, root, right? Oh yeah, totally right. It would be 0 for the first one because by default it would be 0. This is simply reduce the if else statement to one line. It's the if. So this is what's called a ternary statement. Never write these because they're terrible. Because they're terrible to read. They're not very you always want to care about readability, but if you haven't seen it yet, might as well just simply take the time to mention what this is. This is in a lot of C-based languages like C and C++ and Java. Python, I think, just doesn't do that because it thinks it's stupid. Good on you, Python.
In line, you can say like
You can also do ands, and you can do these things chained as well, because of course you can. Basically it's saying, hey, if this is called a ternary statement. So if this statement over here is true, all right, we're asking this question. If it's true, we return the left side of the colon. If it's false, we return the right side of the colon. That's all it is. Ask this question, true gives us the left, false gives us the right. Don't use it because it, can get really hard to read. It's easier to read it broken out into like an if else statement. And always value readability. Always important to do readability first.
There's a lot in UI programming because for a lot of those cases, there's a lot of statements.
Yep. They're useful. It's just like it's when they get really long. That's when they're terrible.
Yeah, we only use it if there's only one. One case.
All right. So next one. Clear all drawings. So I like doing questions about trees by asking about tree properties. Like, hey, write a method which, given a tree, returns whether the tree is a full tree. So this is different because here, mainly because we're going to actually have to ask some interesting questions. First off, you've got to make a judgment call for our base case to begin with. So, right, public static e Boolean. Let's go ahead and do that. Is full tree node e root. Right. So here we've got a tree. So first things first, I got to ask myself, yes.
Quick clarification question. So in the problem, it says node E tree. Does that just mean it's the root?
Yes.
Right. Okay. Because I wrote my whole thing with root and then realized it said tree, and I was like, wait, what?
No, that was just me. That's just my first draft before I
Cool.
and I never went back and changed it because I'm terrible like that. Okay, so first things first, we have to ask ourselves, if the tree doesn't exist, is it full? And I'd argue yes, it's got 0 children or no children, sorry, or 2 children. So okay. So if root equals null, return true. Now, the reason this one is different is because actually we do, in order to answer our question, we do depend on whether or not we have, you know, one of our base case essentially is asking, do my children exist? Right? If I have a left child but no right child, or right child but no left child, then I can immediately return false. Right? Those are base cases as well. If I've got no children. So first, and if I have no children, then I can immediately return true. So if root dot left, so let's start with that. If root dot left and sorry equals null, copy and root dot right equals null, return true. So now I'm going to copy that. And honestly, I'm also going to do else, even though I don't have to because of the return statements, but I like being explicit that these are independent statements. It just is good practice to say what you mean in case you change it later. So here, I'm going to say, hey, what if I have a left child, but not a right child? Well, then you're not complete. You have only one child. Insert social commentary, right, of your choosing. So here I have a left child. Sorry, I have no left child, but I have a right child. Also going to return false. Okay. So there we go. So if I have no children, I'm a full tree. If I have one child, this subtree is not full, so return false. What if I have two children? Oy vey, okay? If I have two children, well, then that's completely dependent on them, right? Because if for this tree being full, I know my subtree is. So, right, and what I mean by that is like, right, if I have two children, then me being full depends on the entire tree being full, depends on them being full as well. Right? So in order for this to be, in order for this guy to be full, for this full thing to be a full tree, this subtree has to be full, and this subtree has to be full. Make sense? That's a lot for a parent to calculate, right? I mean, I've already checked that they exist. So that's the minimal amount of parenting I have to do, apparently. So, so now what I have to do is basically ask them, hey, here I'm just going to do a very simple statement, which is, it's going to be recursive, which is, hey, a return is full tree, root dot left, and is full tree, root dot right. So if my left tree is full and my right tree is full, yes.
Finish your thought, because I just had.
If my left tree is full and my right tree is full, then I'll return true. If one of them is not full or both of them are not full, I'll return false.
I just want to ask a question. I think it still works, but I didn't test it, so I'm just gonna ask you.
Mhm.
But I like basically don't have lines 34 through 38. I made that my else statement. So I checked if both were null, return true, and then I said else if they're both not null, return what you have on line 40, and then I said else, return false.
That's fine.
Okay,
Yeah, you just simply changed up the order. So long as
it still covers all the cases. right?
yeah, that should work so long as you don't go into the if statement while something is null.
Right.
Right? So as long as you're trying, that works out. So here, so the next one is one I am really like, and notice I put extra practice because this one involves two trees, which I'll simply call root A and root B because my naming convention. And this one checks if they're equal. Now, equal doesn't mean they have just the same items. That means that they have the same items in the same place, right? So what I'm trying to say is that I will consider 2, 1, 3 and 1, 2, 3 to be different trees, right? They have the same items, but they're arranged differently. Make sense? in order for them to be the same, they'd both have to look exactly the same. Make sense? All right. So base cases. Base cases honestly are, they help us avoid a lot of ambiguity. That's why I like, they help us, if we can enumerate them, that they help us having to avoid like, oh, but what if they help us avoid all kinds of exceptions, because we're kind of listing these kind of exceptions first. So let's just start with the easiest, with being the kind of laziest we can be. So I'm going to call them, first off, again, I'm going to rename these root, because I like that term much better. So if there, so the first thing that's easy to check, if root A is null and root B is null, they're equal, right? If they both don't exist, well, nothingness equals nothingness, so I'm going to return true. Make sense to everybody? Okay. Now I'm just going to copy this and do a else because I like chaining these again. I like these to be else ifs. They don't have to be, but honestly, it just feels better. Okay. Otherwise, if one exists but the other doesn't, then obviously they are not, right? If one exists but the other doesn't, obviously they're not equal, right? Can't be equal because something is not equal to nothing. It's something, right? Yes.
Could you also just make it one line and use an or since you already checked if they're both null?
Yeah. You could do an or, like you could just do these. I just like enumerating these things like this.
No, I understand what you're doing. I just want to make sure that what I did is also like the same thought
Yeah.
process in a different way.
Yeah. There's a lot of different ways to present logic. So otherwise, so here we have root it. So here they nothing is equal to nothing. Something is not equal to nothing. Something is not equal to nothing. Otherwise, we've got two somethings. Okay. Well, now we can check. Well, now we can still do another base case, but we're going to do it inside here just simply for the sake of this, because we have two, because I like this else being two separate things. So I like this else saying, hey, this is a case where we have two somethings. So if root A is something, call it data. Okay, I should have called it item. That's much easier to type. Root A dot data dot equals. If you did double equals, that's okay too. But the proper way to do it is to use the dot equal statement. So if those two things are equal, great. I'll figure that out. Otherwise, return false, because if the two, right, if I've got two somethings, but I compared 2 to 3 and they're not equal, then the trees are no longer equal. Right? Make sense? So I could also, just invert this and say, if this was not equal, put return false, otherwise do this, but if they are equal, then what do I have to do? Well, in that case, the tops of these are fine. So it's going to depend on my left subtrees and my right subtrees being equal. So if the two roots are equal, then them being equals depends on the root A dot left being root A's left subtree being equal to root B's subtree. Make sense? And equals root A dot, and the right subtree is being equal. Again, the wonderful thing about recursion is that it's, once you get the hang of it, it's not really that hard to write. And the statements you have to write aren't really that complex when it comes to trees. You just kind of just have to just kind of think through all the possible base cases and then figure out what the kind of recursion you're doing is. All right. Been going through this practice exam fairly quickly, which is nice. All right, so next I'm going to move on to maps. Write a method which returns what characters occur in a string and how many times each one occurs. This is fairly straightforward. Okay, copy. This is your standard like word count variation. So here, public static map. So I've got to import that, which I'm going to actually do by importing star because I'm lazy. So here, what I'm going to do is that basically we need a map to return. Map. So we're gonna. This is a map that keeps track of for each character how many times that character occurs. And we'll do a hash map. Now, what we could do if we wanted to ensure that it will print out in alphabetical order, what we'd want to do is use a tree map. Tree map is the same as a hash map, only it uses a binary search tree, self-balancing binary search tree. And that means that all the operations are done in log n as opposed to constant time. Oh no, log n time. That's so terrible. That's so horrendous. Honestly, it really just depends, but hash map keeps track of hash map doesn't care about the order. That is the sacrifice. So for each character C in, now unfortunately, unlike Python, you can't do like for C in Word like this. In order to do a for each loop over over something like this, you have to do 2-character array to turn it into something that you can do a for loop. It's stupid. I don't know why you have to do it like that. Also, let me quash the error by returning map. So what we're going to do, so I'm going to write this the long way, and then I'm going to start shortening it up like you wouldn't believe. Okay, so first thing I want to do is ask, hey, if map dot contains key, and I'm going to say not contain. So if map does not contains the key C. So in other words, if this map doesn't have it, that means I haven't seen this character before. Make sense? So what I'm going to do is I'm going to say map dot put C1 because I've seen it once now. We've seen character C once. Otherwise, I have seen it before, right? If there's only 2 possibilities, I've seen it before, I haven't seen it before. Otherwise, I've seen it before. So what I have to do is I have to get map dot get int sightings. I'll call it sightings. Map dot get the number of times I've seen C, right? And then what I'm going to do is I'm going to say int. I'm going to do map dot put sightings, sorry, C sightings +1. So the number of times I've seen it +1. That's going to be, we're going to update the new value for that. That's all you really ever have to do for this. Fairly straightforward to do a count like this. Make sense? Okay, so how can I shorten this up? Honestly, I've been blazing through this, so want to make sure there's plenty of time to go over stuff. So one thing that you might realize is that this sightings is extraneous because I can just simply put get C in here and it just looks kind of, and it shortens it up like crazy. It just kind of looks meh. Another thing we could do is that basically we could, there is one thing, one thing else we can do, which is get rid of this if else statement entirely. And that's to ensure that, and that's to use a nice method built into here. So we can just do this I'm going to reduce this to 2 lines, and then this if statement to 2 lines, then to 1 line. What I'm going to do is basically I'm going to use the int sightings again. So I want to just get the number of times I've seen C yet. But what if I haven't seen C yet? That's where I'm going to use this function, map dot get or default. So I'm going to get C0. And what this says is that rather than giving me an error if C hasn't been seen yet, give me a 0. Right, so I want to either get the, so you're either going to perform the get operation, or you're going to provide this default value, right? So here that'd be C. I haven't, so the number of times I've seen C, or 0 because I haven't seen it yet. Make sense? And then what I can do is I can do map dot put sightings +1 for C. Make sense? Any questions about the get map dot get or 0? Sorry, get or default. All this is doing is that it is, again, just simply iterating through and getting and saying, hey, either get me the value that exists for C. Normally this would give me an error if C doesn't exist. Don't give me an error, please. If that doesn't exist, I have a plan for it, which is that I want 0 instead. And then we just simply put that amount in. And of course, the next step is, if you want to make it 1 line, is that you take away this sightings variable and just dump it right in there, which is simply saying, get the number of times I've seen it previously, 0 if I haven't seen it previously, +1. And that reduces it to 1 line. Now, of all the solutions, I honestly prefer this one the best, where I've got it split up like this one, because again, making your lines too long. Remember, the person who wrote your code last week, whoever that person was, that was obviously a madman. Okay, that person was insane. It had no idea what they're doing, and they didn't document it. And so the writings they wrote were that of an insane person. So just remember that. So make sure that, so obviously you're not going to make that same mistake. So you're going to make your stuff easy to read, so that future you won't have as hard of a time doing it, right? If you want, so for an example of this kind of thing, just as an aside, and you'll have to excuse the language, because it is the language is built into the code, but it is on Wikipedia, so that's my defense. It's bad defense, but excuse the language, just the language warning. It's nothing too obscene. I mean, it is an F-bomb, but you know, but not like in a particularly awful way. So let's take a look at the fast inverse square root. Now the fast inverse square root was written for Quake, sorry, for in the first person shooter open arena, it's used here, but it was originally written in for, I think, Quake. So here it's also sometimes called 0x 5f 375.9df. It estimates 1 over the square root of x. Now calculating the square root of a number is kind of hard, actually. So often what we do is that we figure that out using something called Newton's method, which is a way of estimating, approximating. Okay. And so to calculate that further, we do that. But anyway, here is somebody figured out for this to kind of use this. It's useful for doing like angles of incidence and reflection and lighting and shading, all the things that make, computer graphics look extra fancy. So calculating these kind of reflections going on over here. So here is the code over here. Okay. And this is the exact code and the exact comments as they are. Now, this part on the bottom, okay, what they're doing over here is a single iteration of Newton's method, as I was describing, which is that approximation algorithm I was talking about. Okay. But over here, right, we're doing some weird bit level manipulation that really needs a better comment than this over here. Okay. And then the algorithm, you can look into that into detail, especially if you're interested in working in kind of graphics and stuff, like, because it's got a magic number. It's like, how do we know what the magic number, because it was a magic number. It's like, this number works really well for this function. Not sure why. Don't touch it. It's magic. If you touch it, we'll create a bunch of all the magic smoke and our machine will escape. So, you know. So yeah, but like, this is the exact kind of thing you don't want to happen in your code. Make your code readable, even if it takes a couple of extra steps. Once you do that, if you really need to optimize it, comment out that code, leave it in there, and then present the optimization, right? Saying it's this is the optimized, but it's equivalent to this thing. You know, always make it easy to read, because again, the person who wrote the code yesterday, a week ago, a month ago, is a mad person, and we have no idea what's going on in their brain, because now you are perfectly sane, I should mention, right? But the person you were a week ago, complete madness.
Right.
So with that, I'm going to go and skip this one over here, but this is a categorization one. I'm not doing a categorization one on the exam. Let's talk about analysis first, because that's important. So what are collisions in hash table? Why do they occur, and how are they handled? Honestly, these kind of two things are like the same question right over here. What are collisions and why do they occur? Right. So a collision is when two things, a collision in a hash table happens when we've got one key and another key, and they both want to occupy the same cozy space. They both put a bid on the same apartment, you know. Now they got to duke it out. So they and how are they handled? Honestly, battle royale seems the popular way to do it these days. But no, why? So first question though is, why do they occur? Right? What are they? They're when two keys want to occupy the same space. Why do they occur? Because the space of the keys is infinite, right? The number of keys we have is infinite. The space on my computer is not infinite. In fact, the biggest array I can have on my computer in Java, I believe, right? Because what argument does Java accept for the size of an integer? What type of argument doesn't Java accept for a type of an integer? Not your question. What argument does it accept? Does Java accept for the size of an array? Accepts an integer, right? You provide like a new type. Then in here, you say how big you want it, and this is an integer. Go ahead and try putting in a long, it's not going to work, right? So assuming that we can put in an unsigned integer, by the way, that brings our possibilities up to around 4 billion. So we can store about 4 billion independent keys or indices in an array. Infinity, last I checked, was bigger than 4 billion. Could have shrunk, God knows what's been going on in this crazy world. I wouldn't be surprised if infinity shrunk, but they occur because the space of possible keys is bigger than the space of your hash table on your computer. Okay, so now how can we handle that? There are two ways we've handled collisions for hash tables, or that we presented. There's a lot of different ways actually. the first two the ways we've approached this though are open addressing. Technique number one for how we handle them. And the second technique is chaining. Okay, so what are these techniques? So chaining, so open addressing means I want to look for the next available space. You know, so if I can't have this space, if I can't have apartment 422, I'm going to go to apartment 423. Make sense? So I'm going to look for the next available space. Okay. Now, what is next available though? However, what makes an open addressing interesting is that what is next can be malleable, right? We can have a different definition. We can change what the definition of next available is. So that's where we have linear probing. So open addressing using linear probing. And then quadratic probing. Well, that latter sounds like an alien's trying to take a probe of your like bicep or something. Okay. So so linear probing defines next available space as literally the next available space. So if I can't have space n, I'm going to look and check space n plus 1, then n plus 2, then n plus 3, until I find the next available space, right? Literally just linearly go up and try to find the next available space. Okay, and once I find that, that's it. And if somebody's trying to find me, they'll check n first because that's where they'd expect me. And if they don't find me there, what they're going to do is they're going to go to the next space, then the next space, then the next space until they do find me. Okay. The other way we can do this with quadratic probing is that if I can't have space n, then I'm going to check space n plus 1 squared, which is the same as n plus 1. And then if I can't have n plus 1 squared, well, I'll check n plus 2 squared. So I'm going to check 4 away from my original space. Then I'll check 3, then I'll check 9 away from my original space, and then 16 away from the original space I wanted, and so on and so forth. Advantage of quadratic probing over linear probing is that it creates less gaps, right? If you have a bunch of keys mapping to the same address, right, with linear probing, you're just basically all kind of creating a big clump of items. With quadratic probing, you're at least spreading it out. Okay. Disadvantage of quadratic probing is that we've added an additional operation if we and we might care about that kind of optimization. Specifically, we've added, what we had was an addition operation. Now we have an addition and a multiplication operation. Just in case, you know, but when we're dealing with constant time, we do really care about those kind of little things. Yes.
Small clarification, but so if n is the space, so like if n is like 42,
Yeah.
that's the thing. Will it do 42 plus 1 squared, 42 plus 3 squared?
Yes. It's going to be do 42.
Okay.
It's going to do 40. So we would look for 43, then we'd look for 46, and then we'd look for 51. Yes.
Is like heap probing ever a thing? Has anyone done that?
Keep probing. No, I don't.
Like if you, instead of probing by like your number plus some thing that increases, instead do the same way that you would implement a heap where it's like 2n plus 1 or 2. Well, then it's like to gain 2 locations, I guess.
There's different ways to do it. I'll go over some different ways once we get through, once I cover chaining. I'll show you on Wikipedia. There's a couple different ways. Okay. Yeah. About my love for Wikipedia. So now chaining, what does chaining mean? Well, in our original form, with open addressing, we're very honest about these things, and we're basically saying for each slot, we're storing the key value pair. Okay, right? Key value, key value. This chaining does not do that. Chaining says instead each slot is actually a linked list, a chain. This is also called bucket hashing sometimes. So this is pointing to the head of a linked list, which is null. So when we add an item, When we have a collision, we just simply add that item to the end of a linked list. But linked lists have size lookup n, and that is true if we, it's lookup is size n. If, and so the hash table would be n, if we let the linked lists grow in such a way that that would happen. But with a good hashing function, basically, we will be able to enforce that all the linked lists are the same size. And if they're all the same size, like a certain, if we enforce our mathematics right with the right load factor, then we can enforce like maybe there's no more than 3 lookups, which is a constant time. Yes. So those are questions.
Oh, yeah, I'm sorry. Oh, shit.
So what other techniques do have computer scientists with too much time on their hands come up with? One way is, yes,
Oh, sorry, I have a question.
yes,
You said the space of the key is infinite because the key could be empty.
yes.
Yes, okay, thank you.
I mean, the key could be, even if we just limit it to like real numbers, there are an infinite number of real numbers. So what we're going to do, so what other functions we have is that we have something called double hashing, where if h of x doesn't work, then we're going to try h of x, we're going to try h1x, which is a different hash function, right? So that's another way. Basically, if the first hash function doesn't work, I'm going to try a different hash function. Okay. Another way to do that is kind of the reverse of what we've been looking for, which is and my friend happens to be a very big fan of that, which is cuckoo hashing. Now, cuckoo birds are horrible birds. They will like kick other birds out of the nest and other eggs out of the nest and put their eggs there for the birds to take care of. It's named after the behavior of some species cuckoo, where the cuckoo chick pushes other eggs out of the or young out of the nest when it hatches. So here, what it does is that the worst case constant lookup, and what happens here is that everybody cooks it. Is it basically everybody? If your space is taken, you kick them out of the space and they move to an alternate location. So the other way, so basically the reverse of how we've been dealing with it. I don't know the specifics because I never did that. There's perfect hashing, double hashing, hopscotch hashing, right? Perfect hash function that somehow has no collisions. This the S needs to be known, where S is, I think let me guess, yep, the set of keys. So in order to do a perfect hashing so that there'd be no collisions, you have to know what you're going to be hashing in advance. Double hashing, right? That's kind of the whole, what I just went over, where you have 2 functions. Hopscotch hashing, no idea what that is, but it's a way to deal with hash. But yeah, as you can see, there's plenty of ways to deal with these kinds of stuff. But like, these are the primary ways: the open addressing and the chaining, and these are the well-studied ones. Okay. What is the worst case runtime for insertion and deletion algorithms of a binary search tree, and why? Okay. So first off, what is the average case runtime? Right. So worst case, so right, the average case runtime for binary search trees is the reason we use them, which is that they're log n for every single operation we do. Add, remove, lookup. The only thing that isn't log is the log time is the size, which is constant because that's just returning the variable, and something where we're literally doing an in-order traversal. No matter what, if you're traversing over methods, it doesn't matter. If you're traversing over every item, it doesn't matter what you're using. That's an O of n. So average time is log n, because on average, what you're going to do is that, like, you've got half the items on the right and half the items on the left. And if you go to the left or right, your search space gets reduced by half the remaining items. So we can do, so if we do a bunch of halvings, then it's log base 2 of n. That's why we like this, because it's really a really easy way to get to what? Oh, sorry, getting the runtime. Worst case scenario though is a tree like this. The quick round fox jumps over the lazy dog. That turns out to be like a horribly misbalanced tree. Or if I get something like 5, 2, 1, 17, 8, 9, 10, 12, 11. When I get an unbalanced tree like this, essentially I'm just creating a linked list with extra steps. Okay, which means the worst case lookup is event. Now, how do I avoid these? The way we avoid this is by having a run, is by creating, is by enforcing self-balancing search trees. Now, there's a couple different self-balancing search trees out there. So let's just, and we'll just for the last couple minutes of class, I'll just simply talk about them for a second. You've got the classic one, there's two classical ones that you learn in textbooks, but again, time constraints, going over them is a bit difficult. That might change in upcoming semesters. AVL tree, which is a so merely knowing that they exist. An AVL tree, which is named after their authors, is a self-balancing binary search tree. And self-balancing binary search trees rely off of using something, a constant time operation called a rotation, which just swaps the left tree, the right tree, you know, the left and right, and it just swaps nodes around. That was a double rotation right there. And it just uses this rotation to keep everything balanced. It takes log n time. If your tree was balanced and then you add an item or remove an item and it's now unbalanced, it takes log n time to rebalance it. So for self-balancing trees, log n operation to alter the tree, log n time to rebalance it, that's still a log n time. So yes.
Is that easy to implement?
Define easy. The rotation operation tends to actually, I've done an operation, this in class where I've had students just implement the rotation operation, and that can be tricky because rotations are, they require a bit of thinking to figure out how to do. But it's not horrible to do. The other one that's for basically students is the red-black tree, named because we add colors to the nodes. Notice here we've got worst case log n time. And basically we just enforce rules where basically every node is either red or black. All nulls are considered black. Every red node cannot have a red child. So if you have a red node, it's got to have black child. Every path from a given node to its descendant nulls goes through the same number of black nodes. And then finally, there's a fifth one where the root is always black. And what you do is that this enables you to basically to have some rules where basically when you insert, there's specific violations that can occur, and then specific ways to fix that. However, implementing like for the add method takes like 40 lines, and same with the delete. So just to go through all those kind of cases. But it's good because it's one of those things that, again, we kind of figure out these things. Now, it says that down here that it's analogous to a B tree, which is another kind of tree, advanced tree. But the other kind of self-balancing tree I like to talk about is this guy, because it gets you thinking. The 2-3 tree, where every node has either 2 children or 3 children, right? We've been dealing with binary search trees, but other trees can exist. No reason why not, right? Here, right, normal node, everything less is go to the left, everything greater is to the right. How does this one work? Well, everything less than A, so A is less than B. Everything less than A goes to the left, everything greater than B goes to the right, and everything in between goes down the middle. Make sense? So that's fairly straightforward there. And then you have specific ways of adding, right? How do we add? How do we insert a node? So for inserting 4, we just add like that. And then we just show that, hey, we added another node to the bottom, but it can't fit, so we have to split it somehow. So there's specific operations that we can do there. All right, so I think I'm out of time. Yes.
I have one more question. Is the tree sets in Java a binary search tree?
Let's go look that up really quickly. I think so. And I said so, but let's double check. Because I would not want to be accused of giving you bad information. So guaranteed login time.
So balance.
Yeah, I mean, be balanced, but I mean, it doesn't say if it's a binary search, if it's a binary tree or not. I don't know if preset, how it works. Yeah, it says it uses a self-balancing tree, but it doesn't say what kind. There's no, so it doesn't specify what kind. Let's go ahead and look at the source code.
Very wild. Yeah, no, I have a Spanish class on Monday from 1 to 2.
All right. Tree set. Navigable map. So we might have to look at a different one to figure that out, but yeah, it seems like we'd have to look at a different one to figure that out because it extends, abstract set. So we'd have to check this dot add all, C add all. Yeah, it seems like these already are, that a lot of these are already implemented for it. So, so not abstract set. Java source code. Yeah, it is difficult, but oh, it says remove all. So so that's my question though. It's got add m.put. So what data structure is it using then for m? Navigable map. To put things into a navigable map. Yes, other questions?
Oh, sorry. If you wanted to check something was a perfect tree, would you run into the same issue as trying to check if it was complete, or you have to like check the whole way?
Nope, just have to check if you'd have to figure, the way I would do it is, oh, so perfect trees have a certain, have a formula.
Oh, okay.
So what I do is figure out the size, figure out the height,
And then just
and then just check. That's the easy way to figure it out for me.
Okay, thank you.
Well, technically, technically, you don't minimize the norm, you minimize the norm.
Control F add.
Is it? No, no, minimize the norm.
Oh, no.
I'm talking about.
Put.
the margin. We normalize that.
Oh, yeah, it's one over.
Sorry?
No, I didn't.
I mean, it'll be in the recording, so.
Oh, yeah, I guess it will be. I didn't.
All right. Take good care.